And we're back. I like to remind myself sometimes about Maxwell's equations, especially because there's enough pieces. If you were watching during the break, you saw me, have to rewrite it a couple times because it's easy to get turned around. Where do the constants go, and what expression goes where? And it's helpful, I think, to remind myself what the pieces are, as far as the named sort of relationships we've seen over the several chapters. First two, I can pretty reliably write down. We've got Gauss's law for electric and magnetic fields. And Faraday's law is nice enough. It doesn't require a whole lot of, but I did get a little bit. It's an EMF, and does there need to be an epsilon? I can't, no, because the epsilon goes in the other place. And it's really Ampere's law that gets all the modifications. Ampere's law, as we originally wrote it, was just mu times the enclosed actual current. But Maxwell's conjecture was that there is an effective current that, or at least that we can use to keep track of the fact that the electric field between capacitor plates is changing as the capacitor charges. There isn't any actual current. It sort of looks like there is. But there is, in fact, a change in the electric field, and that electric field contributes to a magnetic field the same way a current does, which I guess makes sense because a current is created by an electric field. So if there is a changing electric field, it's kind of like there is a current. And if there's a current, we know from Ampere's law sort of generally that there is a magnetic field associated with that. So it's a reasonable thing for, I suppose, for Maxwell to have thought. It took some time for us to experimentally verify it, but we now know that that's a very real thing. All right. Suppose we consider two instances of the YZ plane that are delta x apart. Suppose we consider a special case that there exist electric and magnetic fields as oriented here. With magnitudes that could change from plane to plane, but which are constant, uniform on a given plane. So that's what is being shown here, that those are two sort of drawings of the electric and magnetic fields that we're considering, and they are the same across the plane. That the electric field is uniform on this plane, and that so is the magnetic field everywhere on that plane. On the other plane that's drawn, those two fields might have different magnitudes from this one, but within that plane, they are the same. Again, uniform, plane uniform, we can say. I guess YZ plane uniform. Suppose we consider The purple indicated square. This one. Suppose we ask, for the circulation, we called it, of the electric field on the closed loop EFGH back to E. We know two things. We know what it is. We can write it down. E points only in the Y direction. So only this side and this side, only those two paths, EF, GH, have a non-zero dot product, E dot DL. Along path EF, the electric field strength is constant. We can pull it outside the integral E dot DL, and then we're just integrating DL along path EF, which has length A. And those are in the same direction. Now, the dot product for path GH will be negative, so we're walking GH, but the field points from H to G. But the rest of the logic is the same. So we could, if we wanted to, factor out the A. And yeah, these fields might be functions of time. I don't know. I guess, but as long as we evaluate at the same time, we're good. And that's I guess the left-hand side of Faraday's law. The right-hand side, looking up a second, Faraday's law has to do with the rate of change of the flux. The rate of change of the flux, the magnetic flux, through through the surface bounded by path E, F, G, H. Well, okay, so the flux passing through that surface, flux should be I guess we'll use blue. It really should be purple. Let's talk about phi. B dot dA integrated over the area. Now, if we assume that this purple area is relatively small, small enough, at least as far as delta x is concerned, so that the field Bz, which we know the field is only in the z direction, is constant enough over the square, or I guess rectangle, that we can factor it outside the integral. So we're talking about a particular magnitude Bz times the area of that rectangle. And if we're interested in the rate of change, we assumed the magnitude was constant enough, so we only need one coordinate to specify it, and it is maybe a function of time. It makes sense that it's a function of time because we're about to take its time derivative times the area. All right, so being careful here, we should probably talk about partial derivatives. Because we don't mean to take the derivative with respect to x, only time here. Faraday's law is not a spatial thing, it's evaluated at a point. So, speaking of Faraday's law, equation 1 and equation 2 are equal. Two within a minus sign. Whoa. So we can set them equal. That's z, b sub z. This is Faraday's law. We've got an A on both sides. And let's divide delta x to the other side. We said delta x ought to be small in order to talk about evaluating the magnetic field at a particular spot and calling it uniform. Small, you say. Perhaps you mean that it's approaching zero. We've played this trick before. That's the partial of E sub y with respect to x. Okay, cool. That's interesting. But what does that do for us? Well, we're only half done. Same situation, but suppose we consider a different rectangle. Use a different color for this. Let's do orange. If we're going to ask for an application of Ampere's law. Now, this is a source-free region. I have considered no charges and no currents. There's nothing, there are no charges and no currents. So there's a sort of a modification of Maxwell's equations that we could make in the absence of sources. Really in the absence of charges, because current is just moving charge. So we still have Gauss's law. But now, if there's no Q, the answer is 0. Still 0 for magnetic fields, nothing there. If there are no currents, Ampere's law simplifies quite a bit. Come on. There's no I sub c. There are no actual currents. There is only possible a displacement current if there is a time varying electric field. That's the only possibility. And Faraday's law stays the way it was. All right. So in this current-free neighborhood of space, what happens if we evaluate Ampere's law? Or the Maxwell correction to Ampere's law? Let's consider the circulation around the loop. Different loop, different points, but let's still label them E, F, G, H to follow along. Here again, as drawn, we are restricted only GH and EF experience a positive dot product, or a non-zero dot product even. Path HE and path FG, there's no magnetic field that points along DL. So both those legs of the path have a zero dot product. So we're back doing something very similar to what we did a minute ago. Magnitude of B at EF now we're walking E to F, but the field points the other way. So this gets us a minus sign BZ evaluated at X plus delta X and time T times the length A, B dot DL. And we also have path GH, in which the field and our path direction are parallel. So we get a positive dot product, and it's BZ of X and T again times A. So we could factor out the A and maybe a minus sign if we wanted to. I think you can already see where we're headed. Suppose we consider the other side of Ampere's law. Now, the electric flux through the loop, suppose we again assume delta X is small enough that we can treat the electric magnitude as constant over the area, so that we can pull it outside the integral and write that we're talking about mu zero, epsilon zero, magnitude of the field, which points in the y direction, evaluated at X and T, times the area of the loop, which again is A delta X. And if we follow along with Ampere's law now, equations 1 and 2 should be equal. Again, parameter A cancels. Again, let's divide both sides by delta X, and we end up saying that BZ of X plus delta X and time minus BZ of X and time divided by delta X is equal to mu zero epsilon zero. Oh, wait. D by dt of the electric flux. I just wrote the flux. Again, you gotta watch out. Who knows what I'm gonna write? D by dt, where again, we should use the partials because we're not talking about the rate of change with respect to X. Where again, in order to sort of account for the fact that we assumed that delta X was small enough, we're taking the limit. And again, we have the partial of equal to mu epsilon partial with time. Thumbs up so far?
I think we lost a negative.
Okay. I think you're right. It's just got to go someplace. Let's put it here. This one is the one we lost.
Yeah.
Let's take the partial of equation 3 with respect to x and the partial of equation 4 with respect to time. As long as we do the same thing to both sides, we can do whatever we want. As long as it's not dividing by 0. Partial of equation 3 with respect to x gets us the second partial on the left-hand side, and the sort of mixed partial of the magnetic field. Taking the partial with respect to time of equation 4 gets us the mixed partial on the left-hand side. And mu epsilon, the second partial with respect to time on the right-hand side. Now, I mean, technically, we had, from equation 3, we had d by dt, and we took the x. So that's correct as far as like operator order. We had d by dt, and then from the left comes d by dx. From equation 4, we had it the other way around. We had del x, and we came from the left with del t. But the partial derivatives are commutative. It doesn't matter the order in which we take them. Which means we hop the negative back over. The right-hand side of the partial of equation 3 with respect to x is equal to the left-hand side of the partial of equation 4 with respect to time, which means Now, that should look really familiar. Where'd that wave equation go? There it is. We had the partial with respect to time is equal to some junk times the partial with respect to x. So I gotta put the junk on the x side. But that's the wave equation. The electric field is a traveling wave. Has to be. I have no choice. And that means that the junk that multiplies the second partial with respect to x is the square of the propagation speed, because that's how the wave equation works. A scalar multiple of the one equal to the other, that means the scalar, that coefficient is the wave speed squared. So that means we're talking about a wave, a periodic disturbance propagating through space that does so with a speed equal to the square root of this. Try it. Grab a calculator. It's worth doing. Don't just trust me. Are you? Is that what you got? $2.9986. Tell me I'm not the only one. Is that what you all got?
And that's what I got.
Hold on. What are the units for this thing? I mean, it's labeled V, but I'm like my heart is racing. This is a fucking wild result. What are the actual units?
Meters per second, or at least some distance. I guess, yeah, meters per second.
Because it's a speed.
Yeah.
Yeah. Is that actually true? Like, what are the units for these things? What's the actual unit for permittivity and permeability? Can we go grab them? Just hold on. I'm trying to think about the easiest way to talk about them. F equals QV cross B is a thing we said, right? So a Newton should be a Coulomb meter per second times a Tesla, right? Does that help any? Not really. Well, I need to talk about epsilon. Epsilon and mu. Let's see. B is equal to, well, hold on. It's Gauss's law. Gauss's law is where the units come from, right? E dot dA is related to Q over epsilon. So if we solve for epsilon, it's got to be coulombs over electric field, which I guess would be newtons per coulomb, times meters squared. So that's coulomb squared over Newton meters squared, right? What about mu? Gauss's law here doesn't help, but if we think about Ampere's law, B dot dl was mu 0I, right? So this is Tesla meters mu amps. Okay, so it's Tesla meter over amps. I think I knew that one. All right, but an amp is a coulomb per second. So this is coulomb per second. And a Tesla, see, I knew I needed QEVB. A Tesla is a Newton over a Coulomb meter per second. So this Tesla here, that's seconds. Newtons over coulombs meters per second. Meters over coulombs. The meters cancel, the seconds flop upstairs, and that's seconds squared newtons over coulomb squared. So if we multiply these two things, that's coulomb squared over Newton meters squared times seconds squared newtons over coulomb squared. So we end up with seconds squared over meters squared. And if we take 1 over that, and the square root, it is absolutely meters per second. This is no accident. It's actually meters per second. We just, Maxwell had an idea about symmetry and had a sort of an argument having to do with the changing electric field associated with the charging of a capacitor, and said, it kind of looks like a current. So what if we we're talking about a changing magnetic flux? What if we also talked about a changing electric flux and how it looks like a current? That means electric fields travel through space at the speed that we have measured for light. It seems really out there to claim that there are multiple things that travel with the speed of light, which I think forces us to conclude that electric field waves are light. Am I? What? Wow. What if we had switched the derivatives? We would have ended up with the wave equation for magnetic fields as well. I'm going to leave that to you. We would have ended up with the sort of cross derivative of E and the double part, like the second partial with respect to x of b on one side and the second partial with respect to t of b on the other side, with a velocity in between. Same expression, mu epsilon. So not just electric field waves, but also magnetic field waves. And we couldn't have done what we did with the electric field without there having been a magnetic field as well. That the electric field and the magnetic field together are each other's propagating sort of MO, right? Like the fact that one is changing allows the other to propagate, and vice versa. It is its own propagating medium. There was no string here. there were no currents, there were no charges. This is empty space in which an electric field changing and a magnetic field changing move in the x direction with this speed. Holy shit. The fact that this was a consequence of the formulation of Maxwell's equations revolutionized three fields, three disciplines all at once: light and optics, electricity studies, magnetism. It's all the same. It's all the same inquiry. Light. is an electromagnetic wave? I'm forced to conclude that because light is the thing that travels with this speed that we just sort of calculated, predicted. Oh, to finish our discussion of what I thought was electricity and magnetism, we're going to need to also study the behavior of light and the behavior of waves, frankly. And that's what the next two classes are about.